So then we've seen most of the types in JavaScript now, all these different things down here. We've still not touched on symbols yet, but we will cover that in a later chapter. So now we know a bit more about objects, I'd like to introduce the idea of primitive and reference types. Now, I don't want to get too bogged down with this right now, and we will be revisiting it later, but I do want you to understand the basic concepts. So then, what are primitive types and what are reference types? Well, in JavaScript, primitive types are numbers, strings, booleans, null, undefined, and symbols. So that's 6 out of the 7 types in JavaScript that are primitive types. Now, reference types are the object type. So any kind of object literals, arrays, functions, dates, and all other objects like the math object. These all fall under the object category, the object type, and they are all reference types. So we have primitive types and reference types. But what does this mean exactly? What is the difference between primitive types and reference types? Well, it's all to do with how they are stored and used in memory. So when we create a primitive value like a new string or a new number or a boolean and we assign it to a variable, that value is stored on something called the stack, like this. Now the stack is just a stack of different values in memory, and they can be accessed pretty quickly when we need to use one, but the space inside this stack is quite limited. So when we create a reference type like an object literal or an array, that is stored not on the stack, but on what is known as the heap. Now the heap has more space available, so it can hold bigger and more complex types like objects and arrays, but it's a bit slower too. So primitive types are stored on the stack, which is a bit quicker, and reference types are stored on the heap. That's 2 different parts of memory for 2 different things. But why is this so important? Well, when we store a primitive value in a variable, it adds that value to the stack and it locks the variable name to it as an accessor to that value. So it knows whenever we want to access the variable score, for example, to go out and grab this value for us. So when we store a reference type in a variable like an object, it adds the object to the heap and then it adds a pointer to that object on the stack. So say for example we make an array, it adds that array to the heap and we store this array in a variable. It adds a pointer to that array in the stack and then it locks this variable name names to the pointer. So when we access this variable in the future, it knows to get this pointer which points to this thing on the heap and it grabs that array for us. Now you might still be thinking that this is not important at all, but it is, and it does have ramifications and it will affect the way that we code. So let's just go back to virtually an empty stack and an empty heap. Now imagine we create this variable score1 and we set it equal to a number 50. Now this is a primitive type, so it's stored down here on the stack and the variable name is locked to that value, so when we try to access it in the future it knows to grab this value. Now what if we make a copy of this variable? If we create a new constant called score2 and we set it equal to score1. Well, what that does, because this is a primitive type and primitive types are stored on the stack, it creates a copy of the number and it stores that number separately on the stack. And this variable name, score2, is now locked to this new number. So we have 2 values now, 2 different values. Well, they're the same, but they're 2 different positions in memory on the stack. And we have 2 different variables locked into those. So in the future, if we were to say score1 is now equal to 100, it just updates this value down here, which is attached to the score1 variable. It doesn't affect this. This is still 50. And that's completely normal behavior, probably something you would expect to happen. Now, what if we do this with different types of data, reference types? Well, imagine we create a new constant, user1, and set it equal to an object. Well, that object is then stored on the heap because this is a reference type. Now we have a pointer to that object on the stack and the variable name, user1, is locked in to that pointer. So in the future, if we try to access user1, it's going to find this pointer which points to the object and return this object back to us. Now, if we create a copy of user1, if we say a new variable, user2, is equal to user1, what's going to happen? Well, it doesn't create a new object on the heap this time. What it does is it copies the pointer doesn't copy the object on the heap, it copies the pointer. And we have our new variable, user2, locked to this new pointer. So they both point now to the same object on the heap. So if in the future I now say, okay, well, user1 is now going to get updated, I'm going to change the score to 50. So now this new object is stored on the heap. And what that means is if we access user1 in the future, it's going to get this pointer, which points to the object and bring back this object. If we access user2, it gets this pointer. This also points to the same object, and that gets that object as well. So when we update user1, it's also really updating user2 because they both point to the same object. So this might not be the behavior that you'd expect when you first come to JavaScript. When we make copies of primitive values like strings and numbers and booleans, we make a new copy of the value on the stack. When we try to make a copy of a reference type, we only make a copy of the pointer on the stack, which points to the same data on the heap. We don't make a copy of the actual data. So when we then change the copies, it does have an effect on the original value and vice versa. So let's see what this means in the code. So let's take what we've just learned about primitive and reference types and see it in action so you know when we come across this kind of behavior in the future, what's going on. So primitive values first of all. I have right here a variable, score1, and we've set it equal to 50. Then I'm making a copy of that variable. I'm saying let this new variable, score2, equal to score1. Now remember, that creates a copy of that value and stores it separately on the stack because this is a primitive value. Now down here, I'm just logging to the console a template string where we're outputting score1 and also score2. So let's have a look at this. They should both be 50, right? Score1 is 50 and score2 is 50. Okay, now imagine we changed score1. So let's do that. Let's say now score1 is equal to 100. And now I'm going to just grab this and paste it down here again. So we have it output before the change and after the change. So if we save it, we can see that score1 after the change is now 100 and score2 is still 50. So when we make a copy of primitive values like this, if we change one of them, it doesn't affect the other. Now let's comment this out and come down to reference values or reference types. So down here, I've created a variable, or rather tried to. I'll use a const keyword there and a const keyword here as well. And what I'm doing now is creating a new object, and that has a name and an age property. Then I'm creating a copy of that variable, of that object. User2, we're setting it equal to what user1 is. So remember, this is a reference type, it's an object. So this object is stored on the heap, and we get a pointer locked to this variable stored on the stack. Now when we create a copy, it doesn't copy the actual object, it just copies the pointer on the stack. And then user2 is locked to that new pointer, but they both still point to this same object. Now when we log both of these users out down here, we should see the same object. And we do, Ryu and Ryu 30 and 30. Now then, if I try to change the name of one of these, and I'll just do that by saying user1.age is now equal to 40 or something like that. Then if I copy this again and paste it down here, we can see that now it changes both of them. They're both now 40 because remember, it's only stored once on the heap. So if we change that value, it's changing it on the heap. And then both of these pointers, user1 and user2, are pointing to that same object. So if we update one, it updates the other. And it doesn't matter if I update 1 or 2 here because they're both pointing to the same thing. If I change this to 2, we're still going to get exactly the same result. And we could do something instead like the name. We'll change the name to Chun-Li. So let's do that right here. Save it. And now we can see they both are Chun-Li. Okay? So that is primitive and reference types. This is the kind of behavior you need to watch out for in the future when you're coding, because you might do this at some point thinking that now we have two completely separate values when we make a copy, but in fact we don't because they're reference types and they're stored once with two separate pointers. So that's the basics of primitive and reference types. Whenever this will be affecting our code in the future, I will be sure to warn you.